Okay, continuing on with our study of limits, we're going to look at three so-called famous trig limits. These three examples are typically in any introductory textbook that involves trig and limits. And what happens is once you get into calculus, these guys become smaller parts of bigger problems. We're not really concerning ourselves with the bigger problems today. We're just going to look at these limits as is and talk about how we can handle them. So for the first expression here, we have sine of x over x. And we're looking to see what happens as x approaches 0. Well, this expression is undefined when x is equal to 0. So there's something going on there. Now, in general, limits can be solved analytically, graphically, or numerically. For the math that we know, we don't have an analytic way of getting that job done. There is no paper pencil set of skills that we know that we can apply to this to figure out what the limit is. But as long as we can get it into a graphing calculator, we have a graphical approach we could take, we have a numerical approach we could take. So I already have the graph of this in my calculator. I already have Windows set up where I can see what's going on as x approaches 0. So looking at this particular graph, it appears as though as we trace coming from the left towards that x value of 0, it looks like it's heading to that first tick mark on the y-axis, which is 1. If we trace along coming from the right-hand side, it appears as though it's heading to that same y value of 1. So based on the graph we have in this particular screen, it appears as though the left-handed limit is 1, the right-handed limit is 1, therefore the limit is 1. Okay, let's take a look at the table. So I already have this set up with the key values in a table. So some values we can use approaching 0 coming from the left: negative 0.1, negative 0.01, negative 0.001. And as you can see, 0.998, 0.9999, 0.9, some more 9s. It certainly appears as though as x approaches 0 from the left, the y value is getting closer and closer and closer to 1. As a reminder, the 1 that appears in a table there, that's not really 1, it rounded to 1. The full decimal's down below. All right, as we trace towards 0 coming from the right, values that can be used 0.1, 0.01, 0.001, and you see we have the same thing going on. So graphically, it appears as though the limit is 1. Numerically, it appears as though the limit is 1. If we did have the math tools to figure it out, we could analytically show that the limit is 1. All right, y equals, I already have all three functions in my calculator here. I'm just going to highlight the second one, de-highlight the first one, so I only see the second graph. Something I should have mentioned before I started these problems that I forgot about, unless you're told otherwise, we're always assuming radians. So before I started that first example, it would have been in my best interest to make sure I was in radian mode. I was, so everything worked out okay. All right, anyway, on to the graph. So looking at the algebraic structure, we're concerning ourselves with what happens as x approaches 0. Cosine of x minus 1 over x is our expression that we are concerning ourselves with. Well, we know that this expression is undefined at 0, so something's going on. So to evaluate this limit, if we had the tools that you'll have once you're in calculus, you could examine this analytically. We don't have that option, but we can look at this graphically, we can look at it numerically. So looking at this graph here, as you trace coming from the left, it appears as though we're heading to a y value of 0. As you trace towards x is 0 coming from the right, it appears as though we're heading towards a y value of 0. So graphically, it appears as though the limit is 0. Go to the table. Using the same x values approaching from the left, 0.05, 0.005, that would be 0.30s and then 5, So it definitely appears as though these numbers are getting closer and closer to 0. And approaching from the right, 0.1, 0.01, 0.001, we get the same numbers on the negative side, so that confirms that the limit for that function is 0. Okay, on to the third one. Going to y equals, I'm going to de-highlight y2, highlight y3, hit graph, and we get something going on here that we haven't quite seen before. Everything's looking nice and smooth coming this way from the left, and we get like an angry scribble here, and then it kind of smooths back out again. So what I'm going to do is let's zoom in on what's happening at the origin here, what's happening as we approach 0. So to do this, I'm going to go to Zoom Box, and define the upper left-hand corner of my box, enter, define the lower right-hand corner of my box, enter, and we're still getting an angry looking scribble. So I'm going to repeat that process again. Zoom, box. I am going to define the upper left-hand corner of the rectangle. I am going to define the lower right-hand corner of my rectangle. Hit enter. And the angry scribble continues on. I'm going to do this one more time. Zoom box. Define my upper left hand. Enter. Take even a thinner slice. It didn't quite center it very well, but we still get the same effect. And our scribble is getting angrier and angrier, so to speak. I feel like we're zoomed in pretty far. I'm going to go to my window. We're going from an x-min of negative 0.0001 to an x-max of 0.001. So we're in pretty tight towards the origin here. Let's manipulate that and let's make it 0.00. And then make that last one a 1. And let's do the same thing here. 0.001. Enter. Graph. Alright, so what's happening here is no matter how far we zoom in, we're zoomed in to negative 10 to the negative 11th and positive 10 to the negative 11th, and we're still getting that scribble. Turns out that this limit does not exist. This function is just going to keep oscillating back and forth between positive 1 and negative 1, no matter how tight we zoom in. Okay, looking at the table, as we approach from the left, the negative 0.1, negative 0.01, negative 0.001, we don't get that feeling of it's heading towards any one particular value because it's not. Approaching from the right, 0.1, 0.01, 0.001, again, we're not getting that feeling it's approaching any one particular value. So this is another type of does not exist problem, and it's relatively specific to the trig world where we get oscillating behavior, where it's not going to go to any one particular value. Now, in contrast, it doesn't go to positive infinity, it doesn't go to negative infinity. It's not a jump discontinuity like we saw with the when we saw with the piecewise functions. It's an oscillating behavior here. All right, next thing we're going to do is formalize this stuff as I said we would in one of the first days. And how does this appear in calculus in terms of writing some stuff out? All right, these are the notes I use with my calculus class. So starting off with a limit existing. So putting it in a little bit more of a formal context. The limit as x approaches c coming from the left is equal to capital L. So c is your x value of interest. So the x value of interest for those three problems we just did was 0. The limit as x approaches that c coming from the right is equal to L. So this is saying the left-handed limit is L, the right-handed limit is L. Well, if they're the same L, it means the left-handed limit equals the right-handed limit. Therefore, the limit exists, where L is the same real number for each of the one-sided limits. Okay, a limit does not exist if. So if your left-handed limit doesn't equal the right-handed limit, then the limit does not exist. Now, we've looked at that in a couple of different contexts. One way that this can happen, or one common way this can happen, you can get a jump discontinuity, the left-handed limit not equal the right-handed limit, from a single absolute value equation. Now, just because it has absolute value doesn't guarantee that it's going to be a problem that has a limit that doesn't exist, but it's a common way to get what I want to show you here. So we go to y equals, clear out all that trig stuff, we're done with it. I'm going to type in that expression, 2, and then math num to get absolute value, x plus 1, that gets divided by x plus 1, and then plus x squared. And I'm going to zoom 6 this. So what's happening here is we trace from the left, it's heading right to the end of that particular branch of the curve. As we trace from the right, it's heading to a different spot. So the left-handed limit does not equal the right-handed limit. Therefore, the limit does not exist for that x value of -1. Now, if we had more time, we would explore this whole different things that can happen, mixing in absolute value with other things like quadratics. Unfortunately, we're reaching the end of our time, not only for limits, but for the school year, so we're not going to be able to do a lot with this. There are a couple of simple absolute value problems, I believe, included in tonight's homework, but we're not going to be able to get into anything overly interesting with that due to time. Okay, second thing, unbounded behavior. I know we know what unbounded behavior is, but not necessarily by this phrasing. So for this one here, clear out that function, put in 1 divided by x squared, hit graph. So what's happening here, at 1 over x squared, we have a vertical asymptote at 0. So as we trace towards that x value of 0 coming from the left, the graph shoots up to positive infinity. As we trace from the right, it shoots up to positive infinity. Now here's where we get into a little bit of shades of gray here. Technically, if your limit is infinity, it does not exist because infinity isn't a real number. When you say infinity, what you're doing is giving a description of its non-existence. So it is, depending on the textbook you're reading, the test you're taking, the website that you're looking at, it's acceptable if your answer is infinity to answer it does not exist. But it's also acceptable and preferred in most tests, on most websites, in most calculus situations to be more specific than just does not exist. Positive infinity or negative infinity, if that's appropriate, then that's the phrasing that you're going to be expected to use in this particular class. Okay, the oscillating functions, we just addressed that in our third famous trig limit. Now, the weird functions here, there are some functions that can be created that don't really fit any particular category. So, for This function is equal to 0 if x is rational, and equal to 1 if x is irrational. So what happens is we get a series of discrete points that are bouncing back and forth between being positive ones and negative ones without any smooth continuity. There is no reasonable way to address a limit when you have something like this. Now, other than realizing they exist, in an introductory calculus class, it's not anything that gets explored in any detail. This would be something that's at a way higher end math than anything you're going to be doing this year or in the very near future. Like I said, it's something that you should be aware of. These types of functions exist, but other than knowing they exist, you don't really do anything else with it. All right, the stuff on the bottom, we've already addressed in a decent amount of detail, but using them more as just a summarizing the topic to where we are right now. Limits can be found numerically, graphically, and analytically. There are some problems based on our skill sets. All three options are available to us. Sometimes some of those options might be more convenient than others. One of the drawbacks of the numerical and graphical is if you're looking for an exact solution, you may not be getting it. You can get a really good decimal approximation, but not necessarily the exact solution. The analytically, that's a little bit more powerful in terms of getting exact solutions, but it's a trade-off. It also requires a lot more skill. We have definite types of functions and expressions that are within our knowledge base in order to figure out the limits analytically without relying upon numbers, without relying upon a graph, and we've fleshed those out in detail in terms of which those categories are. And then the last thing that's on this particular note sheet that we've also addressed at a couple different times. The existence or non-existence of f of x at x is equal to c has no bearing on the existence of the limit of f of x as x approaches c. So for this particular problem, the c, that x value is 4. That's the one where something interesting is going on. So as we trace coming from the left, the graph is heading towards that hole, which appears to be at 5. So the limit as x approaches 4 coming from the left is 5. As we trace coming from the right, it's heading to that same y value of 5. So the left-handed limit is 5, right-handed limit is 5, therefore the limit is 5. The actual value of the function is 2. The value of the function has no impact on answering that limit question. There are many problems where they happen to be one and the same, but there's no direct connection. All right, another example. We have that same c value of 4, but a different function. As we trace coming from the left, it appears as though it's heading to that hole that has a y value of 3. So the limit as x approaches 4 coming from the left is a 3. The limit as x approaches 4 coming from another direction appears to be 5. So the left-handed limit exists, the right-handed limit exists, but because they're different, the limit itself does not exist. The limit as x approaches 4 does not exist. Now the function is defined at 4. The value of the function is 1 at 4. That value of the function at that c of 4 is irrelevant to answering the limit questions. I could completely remove that and the limit would still not exist. I could fill in that hole there, the limit would still not exist. I could fill that in there, the limit would still not exist. I could slide it up here, the limit would still not exist. Okay, taking that same thought process over to the one on the left. We've already determined the limit as x approaches 4 is equal to 5. If I remove that point from the graph, that limit is still 5. If I colored in that hole with that point, the limit is still 5. If I slid that point up here somewhere, the limit is still 5. The value of that point has no impact on answering those limit questions. I think that pretty much wraps it up for today. That is it.